scanning electron microscopy is an alternative for light beam. So just to view the microstructures, so far we have been using optical microscopes. Optical microscope is a device to use to see tiny particles, tiny things, and cells, atoms, where we use light beam. Because of some physical phenomena, diffraction, and all those things are relevant to the wavelength of the particular light we use. Therefore, we cannot go beyond that certain limit. So, but electrons can be accelerated for a huge wavelength. So, particles, when you accelerate an electron, you can increase. Okay, have you all heard about quantum mechanics? So I saw Professor Lakshman this and I was explaining you something. What are the things, phenomenon that happens in nanoscale or atomic scale? Things at small scale behave like a quantum particles, right? Okay, this is something like that. When you, at the very high speed, electrons behave like a wave. That's a wave particle dual. Probably you will learn everything in your 10th unit, properties of matter or matter and radiation. Okay, so wait till that. What you see here is the scanning electron microscopy. What you see is here is a spider, which is coated with gold. So normally, for a scanning electron microscope, image to be scanned, it should have some conductivity. Because if it is not conducting, then when you expose with electron beams, it accumulates charges. So that won't give you a clear picture. Therefore, to remove the charges from the surface, we coat with gold or platinum or graphite. So this is, now the sample is ready for scan. So you can experience more of this sort of images, the real time, your hair and eyes, a lot of things are available in this link. You can visit if you have time, right? So what is the difference is, in scanning tunneling microscope, we have a probe, scanning probe, sharp tip. Like earlier I showed you the image. Like this, we have a sharp tip. But in scanning electron microscope, what we have is an electron gun, which fires the electrons. What is the difference is, instead of light, we use electrons. That is the only difference. We cannot move atoms, but we can see up to some certain level in an atomic scale using this scanning electron microscope, right? So, do you have any idea how this scanning colored microscopes makes images? No? Okay. What is nanotechnology and what makes it different? Is atomic manipulation, nothing else. Atomic and molecular manipulations. It was considered as an impossible task. But now it is considered, okay, we can manipulate atoms. You can move atom where you want to.
In a significant move forward in the march toward creating electronic circuits that are thousands of times smaller than today's most advanced technology, IBM is announcing a milestone in the ability to manipulate and understand matter at the atomic level. Scientists at IBM's Almaden Research Center in San Jose, California, have for the first time demonstrated the ability to measure exactly how much force is needed to move individual atoms. Knowing the different forces required to move different atoms will allow IBM's nanoconstructionists to figure out which materials should be used for building devices from the atom up. For example, a so-called sticky atom would be used for something that you don't want to move, like a base that you want to keep in one place, while a so-called slippery atom would be used when you want to build something like an on-off switch that needs to move with ease.
10 or 20 years ago, nobody could imagine that we would have today laptops, cell phones and iPods. I think it's impossible to speculate what nanoelectronics will bring us in 10 or 20 years, but I'm sure it will change our world even more than the iPods we have today.
The force is measured via tiny changes in the frequency of a small quartz tuning fork. This exploration of the realm of atomic-scale structures and devices stands to impact the future direction of information technology. This is Jeff Gluck reporting.
Right. It was an animated video for an atomic manipulation designed by IBM. Right? The second thing is, material at nanoscale shows the special properties which do not show at bulk scale. So gold is no longer gold when you make gold nanoparticles. It will not look like a gold color. You can have different colors of gold, green and red. When you change the particle size, what you see gold color is because of their bulk structure. So when you make the nanoparticles, gold nanoparticles, no longer it looks like a gold, but they look like green and red and different colors. So this is the specialty of nanoparticles. When you have the material at nanoscale, they don't show the properties of their bulk. They're completely different. So that's an added advantage other than the atomic manipulation. So these two are the keys for the nanotechnology, right? So what you see here is two important phenomena that occurs at atomic scale, at nanoscale. So you see, a cube of 1 meter dimension have the surface area of 6 meters square. But this is a simple example to understand the surface increases when you break the particle size to very tiny. So the same object, when you break them into 8 pieces, the surface area increases. Here you have 6, now it is 12. Right? When you keep on increasing the particle size or number of pieces, when you have 0.1 millimeter dimensions bricks or cubes, you will have 2.5x. So it's more than this size of this auditorium or big shopping complex or shopping mall. So that is the biggest, that is the advantage of nanoparticles. So what will happen when you have more surface area? The reaction and something related to reactions are high. So that is an added advantage. So material shows different electric and mechanical different properties, which they do not show at their bulk. Right? Okay, this is another example. Okay, are you all familiar with 1s to 2s to? Right? How to write electron configuration? Right. Hybridization? Yes? Yes or no? Yes, okay. This is all materials have band gap. So for an insulator, this band gap is very huge. A material to be a conductor, it should conduct electrons. So normally insulators have filled valence band. Materials have two bands. One is valence band and the conduction band. To be a conductor, they should have electrons in their conduction band. But these insulators have electrons in their valence band, but they do not have any one of the electrons in their conduction band. Just see, this is empty. So what we have to do is, we have to excite, or we have to shift an electron from this valence band to conduction band to be a conductor, to make them conductors. Right? It is an impossible task because we need to give huge amount of energy. If you apply huge potential to the plastics or something, it will conduct electricity. But it is not an easy task. Right? They will break everything and electrons will be excited to the conduction band. But in semiconductors like silicon, pure element, and titanium dioxide, there are some of the oxides shows semiconducting properties. So something like that, when you have when you expose them to light, the electrons at the valence band will be excited to the conduction band. So they will conduct. And metals, you do not have band gap because the electrons are free to move within the crystal structure. So that's why they are conductors. And what is the specialty of nanoparticle is, you can change the band gap by varying the particle size. So that is why gold looks like red and green and gold. When you have tiny particles, band gap increases so that they can absorb high energy photon. When you have small, okay, are you all familiar with photons? Are you all familiar with photons? Okay, light is considered as a small particle of photons. Now we call them photons. The light at particular frequency have energy of hf, or in lambda, when you say in lambda, hc over lambda. So all photons have some particular energy. So when you change, okay, so for example, if the band gap energy is 1 electron volt, when you have a photon with 1 electron volt energy, they can excite an electron from this valence band to conduction band. So you have a band gap 2 electron volts. Now you have a photon with 1 electron volt. Can you excite an atom from here to there? Do you have enough energy? No. But what will happen is, when you change the band gap, the photon has 0.1 electron volt, can excite an electron from conduction valence band to conduction band. Likewise, by changing the particle size, you will understand what I am saying. Sure? Right. Okay. By changing the particle size, you can excite an atom from valence band to conduction band. Right. Are you all familiar with the exclusion principle? No two electrons can have same quantum numbers. Right. Good. Okay. These are the two basics of nanoparticles. Why they are interesting. So now see, there is plenty of room at the bottom. This was considered as a cornerstone of nanoscience and nanotechnology. It was Richard Feynman, a famous physicist. He was awarded a Nobel Prize, delivering a lecture at Caltech, California Institute of Technology, for the American Physical Society. The title of the talk was, "There is plenty of room at the bottom." If you try to understand the meaning of this title, you don't understand anything, because it's just like an idiom. So just for example, you are looking for jobs. I'm addressing you. If I say there is plenty of room at the bottom, it sounds like somewhere vacancies for you. It depends on the context it has been used, right? This is in my point of view. So, and the term nanotechnology was used by a Japanese scientist, Norio Taniguchi, in 1974. After that, Eric Drexler explained the nanotechnology in theoretical way. So these are the history, bit of history of nanoscience and nanotechnology, right? Okay, this is a copyright image. Richard Feynman delivering a lecture at Caltech, right? Right. Okay. I'm not going to explain you what is nanoparticles and what are the definitions for, because you can find everywhere. Though I have given you a simple definition for nanoscience. What is nanoscience? What is science? What is science? Can anyone define? Okay. What is nanoscience is study of phenomena. Study of phenomena at atomic or molecular scales with a pen and pencil. You don't do anything. You don't do anything in the sense you don't manipulate atoms. You are not doing any experiments. Just take a pen and take a paper, you write and do bang up how structures are various. This is a study, organized study. Science is also a study of organization, how things are working. This is science. Making a tea also a science. There's an order, right? Are you all sure? Making a tea is a science? Yes? Okay. So what is nanotechnology? Whether nanotechnology or whatever the technology, technology is something, application. So practical, what you implement out of some science. Where do science and technology come from? Where do science and technology come from? Can anyone answer? When you do research, only science and technology come. So where do you do research? In laboratories, in institutes. So when you have some science and knowledge, who is there to put the product out? The financial agencies, the government. So where do science and technology come from? It's laboratory or institutes, right? Once we have a good technology, it's a good business, development, economy of a nation, right? So anyhow, the different people used to say different definitions for this one. Anyhow, the key points are there. The study at atomic scale, how they behave from their bulk, and nanotechnology is manipulation of atoms. Right? What is the nanoscale? Nanoscale is generally considered as 1 to 100 nanometers, but it doesn't mean to say that 0.1 or 150 nanometers is not showing nano properties. They are still showing nano properties, but just for a sake of giving an explanation or definition, we have defined 1 to 100 nanometers as a nanoscale. What is a human hair size diameter is 80,000 nanometers. Just imagine. Then, what is the size? What is the dimension of a 1 meter, 1 nanometer? If your hair is 80,000 nanometers, what about a 1 nanometer? Can you just guess?